Welcome everyone to our second talk of the Princeton Robotics seminar this fall. It's my pleasure to introduce all of you to our speaker for today, Nikolai Matni, who is visiting us from the University of Pennsylvania, where he is an assistant professor in the Electrical and Systems Engineering Department. He's also a member of multiple research labs at the university, in particular the GRASP lab that probably many of you have heard of, since it is very much a leading robotics lab in the United States and in the world. As part of Nick's career, there's many highlights to be given. I'll focus on some of the most exciting ones. He's been visiting faculty at Google Brain Robotics in New York City, and before that, he's been a postdoctoral fellow at both Caltech and UC Berkeley. At Caltech, he also got his PhD in control and dynamical systems, and before that, he got both his bachelor's and his master's at the University of British Columbia in Vancouver. So he's really been all over different leading research institutions in the U.S., Canada, and he's given talks internationally, and he's received multiple distinguished awards. I think at least 4 or 5 Best Paper awards at different control theory conferences and venues, as well as some of the most prestigious awards in our field, including the NSF Career Award, the Air Force Young Investigator Award, and the 2021, I think, Control Systems Society Award to young investigators, which is one of the most prestigious career awards that someone can receive in control. So this is it's very exciting, and it's truly our privilege to have Nick here to tell us about some of the leading work that he's been doing at the intersection of learning, control, and optimization for autonomous systems. So with this, I will pass it on to Nick, and I'll just give you all a quick reminder that if you're an undergraduate doing the robotics minor, there is a sign-up sheet that you should remember to sign yourself up in at the end of the seminar before you leave. So please join me in welcoming Nick.
Thank you, Jaime, for that ridiculous introduction. Thanks for that. And thank you all for being here today. Really excited to be here. My first time visiting Princeton. Looking forward to chatting with a lot of you, both this afternoon and after this talk. What I'd like to talk about a little bit today is this question here of what makes learning to control easy or hard, which has really been kind of driving the research within my group at Penn over the last 4, 5, 6 years. I think one of the nice things of coming to visit the robotics group and the folks at Princeton here is I don't think I really need to convince anybody or motivate anybody of the importance of safety guarantees and guarantees of predictability when I'm taking learning-based components and integrating them into safety-critical decision and control stacks. Right? We've all seen the videos at this point of a robot falling over or a self-driving car driving into something that it shouldn't. And so I'm not going to do that. Instead, I'm going to take a little bit more of a pragmatic perspective to try to motivate why we're thinking about this question. And this is, I think, something that's going to resonate with the students in the room, which is this idea of graduate student descent. Right? I think in this modern age of deep learning and deep reinforcement learning, we've all been there. We have this exciting new idea. Sweet, let's spin up some Mujoko environments and see what happens. Of course, it never works the first time, and so our training curve diverges. So okay, maybe I messed up with my learning rate, so I'll try a new learning rate schedule. It helps a little bit, but it keeps turning. It keeps diverging, so I'll play around with how many layers I have. I'll replace my ReLUs with a CellU or a GelU or whatever the activation layer, activation function du jour is. And before I know it, 3, 4 months have passed by, and I've been staring at these training curves and having nightmares about them, right? And the question here is, why is my silly little Mujoko man not running? What is going wrong? Why isn't it working? My very superficial claim here is that there's two things that could be happening. One is, I haven't quite hit on that sweet spot of hyperparameters yet. We all know deep learning, deep reinforcement learning can be extremely finicky, very sensitive to these choices. Maybe if I spend a little bit more time, do a few more parameter sweeps, I'll actually converge to something that works well. Or it could be that the problem that I'm trying to solve in terms of what I'm giving my policy access to and the thing that I'm trying to get my system to do is just fundamentally hard, in the sense that even if some oracle came down from the heavens and handed me the best possible policy, it would still lead to really, really bad training curves or just reward curves. It just wouldn't do well. The issue right now is that we don't have a systematic way of disambiguating between these two scenarios, right? So you don't know if, okay, should I put in more blood and engineering sweat equity to try to get this to work, or do I need to change something about my problem, right? And so this was really one of the kind of key driving motivations behind this question and the title of today's talk. And we're going to spend the rest of today trying to start to give some insights as to how we can maybe come up with a systematic way of disambiguating between these two settings. And to do this, we're going to take inspiration from an area of applied mathematics that is near and dear to my heart, which is robust control. So you may have taken a class here, or maybe, I don't know, I think in Elad's class on non-stochastic control, you might get exposed to at least H infinity or those kinds of ideas. I want to bring to your attention another component of robust control that arguably is one of the most important from a practical perspective, which is this idea of fundamental limits, which says that some systems, no matter what I do, can't be controlled well. They're just going to lead to crappy, unreliable, fragile performance. Right? So another way of saying this is some systems, no matter what controller, all controllers are going to perform poorly. And I want to illustrate this with a very fun example of this idea of balancing a pendulum on my hand using vision. And fortunately, you guys have one here, so I can do it. Right? So this is the task, right? So this is the task that we're modeling mathematically. And we want to try to understand things about the physics and the sensing and the actuation of this that connect to how well I can keep this thing upright. Right? And that's what I mean by fundamental limits. So one notion of a fundamental limit is some characterization of the badness or the hardness of the dynamics. Right, so in this case, unfortunately, the pointer here isn't adjustable, but if it was, I could show you that if the stick gets shorter, it falls over faster. Right? And we can characterize this in terms of an unstable pull. So that's one thing. Right? If I have bad dynamics, it can make things trickier. It doesn't make things impossible, but it just means I have to be a little bit more careful about what I do. Another element, another way in which things can get difficult is in terms of bad sensing. So in the context of our example here, what bad sensing would be rather than looking at the red tip up here, I would put a baseball cap on or something and only look in the middle. Right? What this does is it makes this so that I can't observe certain movements of the stick that I actually need to be able to balance this thing. Right? Mathematically, we can characterize this in terms of an unstable zero. It turns out the farther down I look, the closer that comes to the thing that I actually need to control. Right? And so you can put these two things together, both bad dynamics and bad sensing, to characterize an amplification from sensor noise, my error in estimating how far away the stick is from vertical, to deviations from it. And we can show that this roughly scales like 1 over where I'm looking. Right? So the kind of main takeaway here is from this toy example, but this applies more broadly, and I'm writing this in words, but we can put this all very formally in math as well, is that if I have bad dynamics and I layer in bad sensing, I'm in trouble. Right? This becomes impossible to control. If you're taking a first course in graduate level robust control, this is typically where the story stops. But I want to add in one little new wrinkle here, which we're going to come back to later, which is the idea that you shouldn't give up at this point. Right? I've characterized the fundamental limits of my system. I've recognized that we're in a bad situation. It means I need to change my system. Right? So in this case, I either need to make the stick longer, or a more realistic change here in this case would be to have better sensing. So this toy idea of looking down, I'll just look up. Right? When I started giving this talk was right after the Don't Look Up movie on Netflix came out, and that kind of worked well. But same idea, right? This is I want you to keep this system, this example in mind, and kind of this philosophy here, right, of characterizing fundamental limits and then changing things to get around that, in terms of how we think about things going forward. Right, and so we're going to try to take these ideas and carry them over to the following question, which is what makes learning controllers from data generated by a dynamical system easy or hard? And the informal meta theorem that we're going to spend the rest of today unpacking, that we've converged towards, is the following one, which is that good optimal controllers, so optimal controllers that lead to high-performing, robust systems, right? So not the kind of bad example that I just showed you, those are actually going to be easy to find using data-driven methods. I won't need a lot of data. They'll be very robust to little errors and things like that. Don't have to be particularly clever in terms of choosing my hyperparameters. On the flip side, bad optimal controllers, like the one that I just showed you, not only are they terrible, but they're also going to be very, very hard to find using data-driven techniques, right? So not only do I have to invest a ton of energy to find them, they're not going to do very well. This may seem like a negative result, but it's actually kind of positive, right? It tells you that if you're in this situation where things are swinging all over the place and your training curves aren't converging, it suggests that maybe you're in one of these situations and you need to change something about your problem. Okay. So with this high-level story in mind, here's the roadmap for the rest of today's talk. We'll start with kind of getting the bad news out of the way and start thinking about fundamental limits, what makes learning controllers from data hard. And we're going to ground this in a very simple class of systems, linear systems, and we'll go through what those are in a little bit. As we get there, I'll also highlight some of the positive results that we've had in this area over the past 5 or 6 years, and kind of explain what they characterize and what they're missing, and how we can actually show you that there are some linear systems that are shockingly benign looking that are in fact very difficult to learn. Once we got the bad news out of the way, we'll move over and start thinking about what makes learning controllers easy. We'll think about things in the general nonlinear setting, but to keep things concrete and tractable, we'll use imitation learning as a case study to kind of ground these ideas. It's a very nice setting where you can think about learning and its interaction in closed loop and decisions without having to deal with some of the more complicated bells and whistles that are involved in, say, reinforcement learning. Then, not sure if we'll have time for this. It'll depend on how many questions happen during the talk. I'll also kind of hint a little bit, just a very short vignette on some recent results we have in leveraging big data from related tasks to do things like multitask and transfer learning, and what that looks like and how things change when you're doing this in a dynamical systems setting. Let me just ask really quick, since we started at I think I started at 11:10, when should I try to end at?
I think if you can aim for 11:50 or
11:50, okay. If you give me 11:55, I can probably make that work. 50 will be a little tricky. Okay, cool. So the good news is this is a pretty modular talk, so if we have to skip the last vignette, we'll skip it and I can talk with folks offline who are interested. Okay, good. So let's dive into this first part of what makes learning controllers hard. The way that we got started in terms of thinking about this line of inquiry was we asked the question, okay, we know we have these systems that are hard to control. It's not clear a priori that they're also going to be hard to learn, right? To control, right? Maybe there's this bad controller that I can find very easily using data-driven techniques. And so that was the first thing that we tried to figure out, was does this carry over? And we did this from an empirical perspective. So we took this exact system and we built it in PyBullet. And the way that we're introducing this idea of quantitative control hardness in this problem is this black bit at the top there, our controller doesn't get to see it, right? And so by controlling how much of this rod is blacked out, we can control quantitatively the easiness or hardness of our control problem. And in fact, we're giving the controller a little bit of an advantage here, because the theory says that I should black out everything except for this little dot at the end of the stick, and we're actually letting it see the whole thing. Right? And then we just applied vanilla, kind of out-of-the-box, soft actor critic reinforcement learning to this system. I think we did 3 different measurement models. One was I just gave it a measurement of where the tip of the stick was, and then another one where it got RGB values, and another one where it got depth values. And they all exhibited the same qualitative trends, and I'll give you a representative example of what this looked like in the following curve here. Right, so what I'm showing you on the right, on this plot here, the x-axis is the episodes of my reinforcement learning algorithm. The y-axis is the running reward. And the idea here is if I get up top to 500, it just means that I'm able to keep the stick upright. Right, this isn't a notion of an optimal controller or anything. This is just how we built up the reward. And I'm showing you different curves here for different varying lengths of this notion of fragility, of control hardness. Right, and so they're color-coded along this. And the way to read this is going from left to right, I'm going from an easy-to-control system to a hard-to-control system. You don't have to be a PhD or a professor to look at this and see that there's something correlated here, right? Something's going on. There's a very striking relationship between how easy or hard to control the system is and the related training curve, the rate at which it learns. Right, so in black here, this is the easiest setting. Nothing's blacked out. It shoots straight up. And as I black out more and more of it, the learning rate gets worse and worse and worse until eventually it doesn't even learn anything. Right? And so for us, this was very exciting in the sense that it indicated that bad optimal controllers are also hard to learn. And I should mention that for each of these settings, the actual optimal controller still was able to keep the thing upright. Right? So this was our starting point. And what I want to spend the next 5-10 minutes on is showing you a stylized theory that captures what's going on here. And to do that, we're going to consider this problem of learning to control linear systems. Also, I should mention, if there's any questions at any time, please feel free to interrupt me. Yeah. So we're going to consider this problem of learning to control linear systems. I want to make sure that we're all on the same page. So these are the system dynamics that we're going to be considering. X is the state of my system, so this could be the configuration of my robot, the state and velocity or generalized versions thereof. U is going to be my control input, and W is going to be some disturbance process. And so what the learning task in this context is going to be, or what's unknown about this system, well, I'm going to assume that I have known A and B functions, but that are mapping some unknown parameter to these system dynamics. Right, and so what this allows me to do is it allows me to fully capture if the system is completely unknown, then A and B are just completely unknown. But suppose I have some physics model for the system, and what I'm trying to learn from data are certain parameters or things like that. I can put that structure into this setup. That's what this allows me to capture. Okay, and then last but not least, we're just going to make our noise white and time Gaussians, zero mean Gaussians. This can be generalized a little bit. It doesn't change the theory a whole lot. And the control problem that we're going to consider is LQR optimal control, which you can think of as kind of the least squares of optimal control. The goal here is to compute a feedback policy that gets access to the state at every time that tries to minimize a steady state variance of a weighted sum of my state deviation and my actuation. All right, so what this cost is capturing is the amplification of this noise process to things that I care about, both in terms of deviation from some set point, as well as the energy that I need to put into the system to keep me there. The reason we like this problem is if I know A and B, if I know the full system, then I can write down closed form expressions for everything. I can tell you what the optimal cost is. I can tell you what the optimal policy is. I can write down nice formulas in terms of the Riccati equation for each of these terms. And on top of that, the optimal policy has this really nice structure. It's the static state feedback. So at time t, I look at the state x. I multiply it by a fixed matrix k that's determined only by my system. That's my control action. Right? So linear systems and LQR are useful benchmarks. They are not a panacea. They do not capture everything. But they're simple enough to analyze, so we can say a lot of things about them. And we'll see here that they actually can capture surprisingly rich behavior. And especially if I'm thinking about or worrying about fundamental limits, lower bounds, then if I can show that learning to control linear systems is hard, automatically implies nonlinear is hard as too. Right? Okay, so this is the general setup, and let's specialize a little bit in terms of setting up the learning problem. So for this first part, we're going to consider the problem of learning an LQR controller from offline data. So what does that mean? This means that our learning process is going to be conducted in two phases. There's an offline phase where I get to run experiments. And the reason we're calling this offline is I'm not penalized or judged on what my system is doing during this experiment process. All right, so as a reminder, I have my unknown system. And during this process, I get to pick an exploration policy. And I just want to highlight that in this setup, we're allowing this exploration policy to be adaptive. It could look at the history of states that it's generated and update accordingly. The only constraint that we're putting on this exploration policy is that it has a fixed energy budget. What this is roughly saying is that on average, at each time step, I get to inject sigma u squared energy into my system. For linear systems, if you don't put this budget, it becomes a trivial problem. Okay, so this is my experiment phase. This is going to generate a data set. This data set then gets fed into a synthesis phase, where I use this data set to output a candidate controller k hat that depends on this data, and I play the resulting policy. Right, I want to emphasize that at no point in any of this am I imposing any kind of constraints or restrictions that any of this has to be computationally tractable. We're looking at this from an information theoretic lower bound perspective, and so you can do whatever you want here. You need to just obey the structure that we've laid out. So the first thing that I'd like to do before we get to the bad news is give you a little bit of a highlight of the good news in terms of what are some positive results in terms of analyzing this problem. Okay. So the first thing I need to tell you about is how we're going to judge the merit of our learned policy, k hat. And we're going to do this in terms of this expression called an excess cost, which is a very natural measure. Right? I'm going to look at the cost that my learned policy achieves, and I'm going to subtract off the optimal policy from it. Right? And I'm just going to call that the excess cost. Right? My excess cost is 0. I've matched the optimal control, the optimal behavior. And if it's small, I'm close to optimal. So here's a flavor of what a positive result would look like. And this is collectively developed within the learning for dynamics and control community over the past 5 or 6 years, and I'm just giving you a representative flavor of it, which says that with high probability, my excess cost will be small if I have enough data. Right? Roughly speaking, that's what this is saying. And importantly, the enough data scales benignly with the underlying dimension of my system and the desired accuracy. And so for those of you who are well versed in learning theory, this is roughly showing that LQR is pack learnable. And just as an example of a typical implementation achieving this bound, suppose I had a fully unknown system, so A and B are completely unknown. The experiment phase, don't have to be particularly clever, just injecting white noise with this prescribed energy. Collect the data set, solve a least squares problem to get estimates A hat and B hat, and then apply what's called certainty equivalent control, where I pretend that A hat and B hat are the true system, and then just proceed as I go. You can show that if you collect enough data, this will be stabilizing, it'll be near optimal, it'll do everything that you want it to do, and even in some very precise senses, in a very precise sense, this is statistically optimal. You can't really do much better than that. Okay. So, as a summary, this is our positive result for learning LQR. Now, you may be wondering, this first part of the talk was supposed to be about hardness results, and I've just shown you positive results, that this is easy, right? I've also been conspicuously silent about this term hiding here, which is typically in the literature called a system-theoretic constant that depends only on the underlying properties of the system. Now, there's an implicit assumption in the literature, which is that this constant is actually a constant. It behaves like a constant. So what I'll show you now are an interesting class of systems, so not pathological. We haven't cooked this up to be by taking limits or anything like that, where this constant is actually not a constant, right? And that combined with some information theoretic trickery is what allows us to connect information theoretic lower bounds with these control theoretic hardness results. And so that's the agenda for the next few slides. So here's how we're going to characterize this idea of hardness of learning to control. We're going to ask for instance theta for a particular system, what is the best possible performance by any algorithm? Right? Now, maybe a natural way of trying to formalize this would be through some kind of pseudo-optimization type thing, right? Where I ask, I want to minimize the excess cost for my system over any possible algorithm. I'm using this alg here as a placeholder. Very intuitive, you would like to do this. Unfortunately, this is not something that you can work with. And the reason for that is there's this kind of pathological thing where my algorithm can cheat. And because I'm allowing the algorithm to be anything, no matter what the data is, it can always just spit out the optimal controller. Right? So this is a well-recognized issue in information theory of these kinds of issues. And so the way that you get around this is by slightly dilating the problem. And instead of looking at this problem, you look at what's called an epsilon local minimax excess cost, right? Which is a mouthful. But really all this is saying is, rather than asking for the best possible algorithm for a particular instance, I want one that works on that instance and a small ball of instances around it. So this precludes it from cheating in the way that we have up there. But by tuning the radius of this ball, I can still get local bounds that are relevant to the particular system or class of systems that I care about. So with this framework in mind, here's an informal main result that I'll unpack and make a little bit more rigorous on the next slide, which says that if I have enough data so that things are well posed, I can lower bound this minimax excess cost, this hardness of learning to control, in terms of a very interpretable quantity, where the numerator is something that captures how easy or hard it is to control my system. The denominator captures something about how easy or hard it is to excite the system and get information about it. Excuse me. And T here is the amount of data that I've collected, right? So at least as a sanity check, the more data I have, the smaller the risk, right? Okay, so I'm just going to take this minimax excess cost and put it on the next slide and write it out in math. And then we're going to unpack and kind of interpret this math a little bit. So I recognize this is there's a lot of symbols. They're color-coded, so we're going to go through each term and try to interpret what they're doing. Those of you who are well-versed in information theory, you might recognize a Kramer-Rao lower bound, Fisher information type of thing lurking here, right? And that's exactly what we did. So this term in green on the right is the derivative of the optimal controller with respect to the underlying parameters of the system, right? So this tells me if I jiggle my system a little bit, how does the optimal controller change? Another way of thinking about this, another way you can interpret it from our perspective is, if I make a small error in my learned parameters, how does this affect the estimated controller, Right? So this captures the sensitivity of my controller to errors in the learn parameter. Now this term is being hit by this expression in cyan, which is capturing the transfer of these errors in my controller to the actual cost that I'm seeing. Right? So the product of these two things is capturing this idea of easy or hard to control. If this thing is small, then life is good. And if this thing is bad, then that tells us that we have a very fragile system where it's very, very important that we get all of the parameters just right. I'm only going to really focus on the numerator. There's a term in the denominator, which I'm just going to call the SNR. And this captures how easy or hard it is to excite the system using an optimal exploration policy. And so what this does is it suggests a strategy for constructing hard-to-learn to control instances. What we've done here is we've connected control-theoretic quantities to information-theoretic lower bounds. So this holds for any system that you give me. And I'm just going to give you some examples of some systems for which this expression blows up on me in a kind of nasty way, right? Kind of showing that there are systems that are indeed hard to learn. And so the class of systems that I'm going to propose that we look at, because they're kind of interpretable and we can work with them analytically, are what we're calling high-gain chains. So what do I mean by that? So here are the dynamics matrices. And the reason I'm calling it a high-gain chain is you can think of this as a chain of subsystems with an actuator on one end, right? So that would be the b equal to 1 at the bottom here. And so if I were to apply a control action, it would enter as this blue square at the bottom here. And it would propagate up the chain. And every time it propagates up a step, it doubles in size. Right? So that's why I'm calling it a high-gain chain. I'll just note a couple things about this system. It is open-loop stable. Right? The eigenvalues are all 0.9. So if I don't do any control, this isn't going to blow up on it. It'll have bad transients, but it's a stable system. And also the 2 on the super diagonal, it doesn't have to be 2. It's just anything bigger than 1. Right? This just leads to nicer numbers. OK. For our learning problem, I'm going to even assume that we know A, and I only need to learn B. And just so that you know that I'm not cheating, all of the control costs and noise variances and everything are just, they're just 1. And so if you kind of grind through this formula that I had on the previous slide, you can lower bound this minimax excess cost as something that is exponential in the state dimension, that's exponential in the length of this chain. Right? So from a learning theory perspective, this is a proof of hardness. Right? My thing goes from polynomial complexity to exponential complexity. And the intuition here is that we've cooked up a system where small errors in my learned policy are amplified exponentially as they propagate up the chain, and this leads to really suboptimal behavior. Right? And so again, if I think of this red square here as an error introduced in my control action, it's going to, just as before, blow up as it works its way up the chain. And I eventually end up incurring a 4 to the n suboptimality. I guess a couple of quick comments before I move on. This may look like a kind of artificial theoretical construct, but these kinds of systems actually do pop up in practice. So I'm working with a collaborator at Penn thinking about soft robots. Right? Soft robots, typically you start with a continuum model and then you discretize them using like finite element methods. Turns out what pops out is something that looks a lot like this. Under-actuated kind of chains of discrete elements. If you think about vehicle platoons, right? Folks from the control side of things, if you remember like things like string stability and things like that, this is roughly what these dynamics look like, right? So yes, a theoretical simplification, but adjacent to, I think, practically relevant questions. So what I just showed you was a hardness result for this offline LQR problem, and I just want to mention that we have a whole other body of work considering different kinds of problems that also and corresponding lower bounds. So Elad, for example, has pioneered some really nice adaptive online results. Not looking at this exact problem formulation as him, but rather just taking this LQR problem and thinking about it adaptively. We can show a hardness result for a lower bound result that has a corresponding hardness lower bound for adaptive online LQR, where now it's on regret. Right? Where the regret is I'm comparing my running behavior to that of a clairvoyant baseline. Turns out it's kind of the exact same intuition, the same kinds of systems get you into trouble there. But there the issue is with online adaptation, I have to balance controlling my system and probing it for information. And this is a system that is hypersensitive to this probing. So as soon as I have to probe it, I incur this exponential loss in performance. The other thing you might be asking is, okay, well, maybe you're just asking too much for an optimal controller. What if I give up on optimality and just ask for stabilization? Turns out you can also get into trouble in that context. There, the hardness to control goes away, but the sysid easiness or hardness is where the bottleneck comes into play. So basically, if I take the same system that I had previously, but rather than having 2s on the superdiagonal, I put a half, and I have something at the end of that chain that I need to identify to stabilize my system, I get into trouble, because it becomes exponentially hard to excite that component of the system. Right, so I'm not expecting you to follow all of the details here, but really what I just wanted to show is that this body of work conveys an overall message of underactuation and ill conditioning can get you into trouble. Right, so I have an underactuated system that's either too excitable or not excitable enough, depending on the setting that I care about, then I'm going to get into trouble, and it might be hard to learn to control the system. And so if we kind of zoom back out and think about our meta theorem, we've addressed the hardness part. Right, we've shown this story here. And before moving on to the next part and talking about the good news a little bit, the one thing that I want to mention is kind of circle back to this idea of co-design, of changing my system. Right? So your controller is hard to learn. Suppose that you figured out that you're in one of these bad settings. Now what? Well, it turns out that we have a paper that's appearing at CDC this year looking at active learning type questions that actually produces matching upper bounds. Right? And so these matching upper bounds suggest that going after either of these quantities can bring you from a hard-to-learn situation to an easy-to-learn situation. So for example, if my system is too excitable, and I have some control over the physics, maybe I can add some damping. And actually, this was nice to hear talking to my collaborator. This is what folks in soft robotics actually do. They'll put damping in the system. If my system isn't excitable enough, then maybe I need to build more actuators. Maybe I can't, but if I can, I should try to do that. Right? And so I don't have an answer to this, but I think it suggests a really interesting question, right? With this idea of co-designing a system's hardware and its kind of control infrastructure so that it's provably easy to learn to control. I don't have good answers. I have intuition. I think it's a really cool question, though. OK, good. So I have about 17 minutes left. So we're actually doing OK on time. So what I'd like to do now is shift from this bad news and move over to some good news settings, right? So we saw the kinds of systems that can get us into trouble. What kinds of systems might actually be easy to learn to control, those that aren't going to suffer from these challenges? And I want to use imitation learning as a case study here. I don't want to assume familiarity with imitation learning, although I'm sure many of you are experts and know more about this than I do. But I'd like to give you just a kind of quick overview of the problem setup before diving into our particular results. So imitation learning consists of the following setup. I have some expert policy that I like, but for whatever reason isn't scalable enough for the setting that I care about. It could be a human. It could be some computationally heavy algorithm like nonlinear MPC or ILQR. And I want to distill this into something that's more scalable, these days typically a neural network. Right? And so the approach is to collect a data set of labeled pairs composed of actions, pi star, and states x of t. Right? So state x of t is the state, and pi star of x of t is what my expert does at that state. And then I just solve a regression problem. Right? I just try to find some pi hat that mimics my expert as best as possible. Right? For this part of the talk, we're going to need to keep track of who's generating the data. So I'm going to use blue for expert data, and I'm going to use red for my test or learn policy. It'll just help alleviate a little bit of notational burden. So I solved this regression problem. I'm using a norm here, but you could use whatever fancy loss function you want. And what comes out is a policy that's defined in terms of this data set D. And the simplest version of imitation learning just takes this policy, deploys it on my robot, crosses my fingers, hopes for the best. More sophisticated versions will then collect this new data, kind of fold it back into the mix, and do some stuff with that. And I'll talk a little bit more about these more sophisticated versions in a little bit. But the first thing I'd like to do is both explain why imitation learning is interesting and what are the challenges. Right? So Jaime mentioned that I did a little stint in industry with Google. During my time there, everything they were doing behind the scenes was imitation learning. Mostly because it's the only thing that people really know how to get to work reliably. When it works, it requires much less data. Reinforcement learning is a lot more challenging and a lot more finicky in terms of just the different kinds of things that you need to tune. The challenge, though, is sometimes it doesn't work. And I want to highlight what goes wrong and how we can maybe go about fixing those issues. So suppose I'm a theorist and I want to reason about the quality of this pi hat in red that comes out of my imitation learning problem. using standard learning theoretic techniques, I can give you the following guarantee, which in words is saying that with high probability, my learned policy will match my expert policy on the data generated by my expert, right? Because that's the data that I had when I actually solved my problem. It's nice, but unfortunately, that's not what I care about, right? What I actually care about is that my learned policy matches my expert policy on the data generated by my learned policy, because that's what I'm actually going to be deploying, right? And this is the difference between classical supervised learning and taking my learned component and putting it into a closed loop system. And so why is this an issue? It turns out that you can have a compounding effect of small errors that lead to just catastrophic failure. Even though your learning problem looks really good, you deploy it and things just go crazy. And I wanted to show you a little cartoon representation of this to make sure that we're all on the same page, because this is kind of the crux of what we're thinking about here. So suppose these are my expert trajectories, and I'll use this cloud here as a cartoon for the training distribution. I run through my imitation learning algorithm, I get my learned policy, and then I have a new initial condition, let's say at this black dot here, that I want to test my new policy on. Now my expert would go in the direction of this blue arrow, and my learned policy will do a decent job of imitating it, and it'll get me close to where the expert would have taken me. So now I end up over here. My expert knows what to do. I'm still within my training distribution, so my policy still knows what to do, and it just makes a small error again. Unfortunately, despite the fact that both of these errors were quite small, the compounding effect of them is that I've now been kicked out of my training distribution. So whereas my expert policy might know what to do, my learned policy hasn't seen this data before, so it makes a bigger error, which kicks me even further out and leads to catastrophic failure. I am not the first person to recognize this. This is really the core of what people who work on imitation learning worry about every day. So what is the new spin or the new angle that we're going to bring to this problem? We're going to try to ask the question, how does an expert affect the sample complexity? What is it about this expert policy that makes this work well or not, depending on the scenario and how much data that I need? So before I can convince you that I have something new to say about this, I should tell you about how people have been thinking about this already. So what I just explained to you is what's called vanilla behavior cloning, this idea of just solving a supervised learning problem and deploying things. That's sensitive to this covariate shift due to this compounding error. There's been broadly two families of approaches for dealing with this. There are what are called on-policy approaches, with Dagger, for example, being a representative, well-known instance of this. And the idea here is, roughly speaking, as my learned policy starts to deviate and make some errors, I'm going to let my expert come in and correct it. I'll take this new data, fold it back into my training algorithm, and kind of rinse and repeat. There are also off-policy methods. The DART, for example, some folks from Berkeley did this. And the idea there is I know that my learned policy is going to make some mistakes. So why don't I inject some noise during training to preemptively kind of puff out and expand my training distribution to hopefully capture the mistakes that my learned policy will make so it'll know what to do. The key idea, at least from my perspective in both of these settings, is I'm trying to show my learned policy how to recover from errors, right? Be it either through corrections or through just kicking my expert around and seeing what it does. There is an implicit assumption here, though, right? Which is my expert can recover from errors. Right? If I don't have an expert that can recover from errors and I ask it to correct things, it'll blow up. If I start kicking it around during training and it can't recover from errors, it's not going to work, right? And so this is implicit. Let's make it explicit, right? What's another word for can recover from errors? Robust, right? So let's think about the role of robustness in my experts in imitation learning and how that maps to sample complexity. So a couple of slides of math, and then we're going to get to some pictures. So why is this idea of robustability important? How can we formalize this? In this context, again, we're going to be thinking about a nonlinear dynamical system. X is my state again, U is my control input. F can be a generic, we're making very minimal assumptions on that nonlinear dynamics F. Only thing here is a certain degree of smoothness in F. Right? So in general, if anybody starts showing you sample complexity results, there's a Lipschitz constant hiding somewhere. For us, the Lipschitz constant is an F. The system is also very, it's deterministic with the exception of the initial condition. Right? So we're going to draw initial conditions during training and during test time. And this is what we want to generalize over. It draws over this distribution of initial conditions. And again, just as a reminder, blue is going to be for my expert data, and red is going to be for my test data or my learned policies data. We're going to characterize the quality of a learned policy in terms of this imitation gap, which is just looking at the worst case difference between the trajectory induced by my learned policy and the expert policy, and learned policy in red, expert policy in blue. So if this gap is, let's say, less than or equal to epsilon, this tells me that my learned policy stays within an epsilon tube of the expert policy's behavior. Okay. So our starting point is a very simple observation, which is that I can take a test policy and rewrite it as a perturbed expert. So what do I mean that? I'm going to take my test policy in red, and I'm going to rewrite it as my expert policy plus a perturbation. And this perturbation is just the mismatch of my learned policy and the expert policy. Right. I want to emphasize that this is a little bit of notational trickery, but the x's are always in red here, right? So I'm not cheating. This is still the data generated by pi hat. Right? And that's really the data that we care about offering guarantees on. And so with this notation and this new interpretation, I can revisit my gap and think of it as capturing the difference between a nominal trajectory generated by my expert and a perturbation thereof. Turns out this idea of bounding the gap between a nominal and perturbed trajectory is an extensively well-studied notion in nonlinear robust control. And it's addressed using a tool called incremental input to state stability. So I'd like to introduce that next and show you how we leverage that. So incremental input to state stability, or delta ISS, at least the way in which we're going to use it, is as follows. Again, remember, red is my test data, blue is my expert data. I'm going to say that an expert policy is incremental input to state stable if for any t I can deviate, I can bound the difference between a perturbed version in red and the actual nominal version in terms of two components. One component I'm going to call a forgetting factor, and another one I'm going to call a robustness factor. If there are any nonlinear control experts in the room, robust is the KL infinity function, and forget is the KL infinity function, and robust is the K function, class K function. Okay. So what is the forget factor saying? This is basically just saying that eventually my system needs to forget its initial conditions. So it's a notion of stability in trajectory space as opposed to a single point. And the robust factor is quantifying the robustness of my system, which basically to perturbations, which basically says that if there are bounded disturbances, they're going to have bounded effect. And the effect to which these perturbations affect the deviations is captured by this robust function. Since we're only going to be comparing two trajectories starting from the same initial condition, this is the only property that I need. I only need this robustness factor. I don't really care about the forget factor, although typically these two kind of come in pairs. And so what we're able to show fairly straightforwardly, almost definitionally, is that if my expert policy pi star is delta ISS with some function robust, then I can upper bound my gap in this way here. Before kind of moving on and working with this expression and seeing what this actually gives us, I just want to comment that this assumption is extremely, extremely mild in the sense that I'm not saying anything about how well behaved this disturbance attenuation function robust is. It could just be a really nasty function. This still holds true. Typically, well-designed systems will have things that scale like linearly or thereabout, and that we can kind of deal with. Okay. So how do I deal with this distribution shift issue? So this is just exactly what we had on the previous slide, which shows that I can upper bound my imitation gap in terms of some function of my expert's robustness, acting on my policy mismatch under this test policy pi. The issue, though, here, right, is the compounding errors affect this term here. So I have no guarantees that that term remains bounded. So that's where the work is going to come in. And our first result was showing the following, what we're calling adversarial criterion for generalization. And what this is asking us, what this is asking from your learned policy is, rather than just matching the expert data, the expert policy on the expert data, I want to match it on a tube around it. And the degree of mismatch which we can tolerate is matched to basically the inverse of the robustness of my expert. Right, so intuitively what's happening is if I have this guarantee within this tube, if I get kicked a little bit, the robustness of my expert kicks me back in. Right, so I'll bounce around within this tube, but I'll never have this compounding error. Right, this is just formalizing that in math. Right, and so this allows me to guarantee a small imitation gap. So a couple of things, and I'll wrap up in 3 or 4 minutes here, I promise. One is that you could just use this as a loss function. If this was something that was tractable, that you had an oracle for your expert that allowed you to query it to actually tackle this min-max problem, you could use it. That's kind of asking a lot. Also, if anybody here has tried to train a GAN or something like that, where you're actually doing a min-max in deep learning, a nightmare, right? So theoretically, a really nice observation, but not a practical algorithm. And so that's where we kind of push things a little bit forward to see if we can actually make this a little bit more actionable. And that's where this idea of a Taylor series came into play. And the high-level idea is we took our perturbation defined on the test data and expanded it around the expert data, right? So the reason we like this is the terms on the right that have these blue arguments, they depend on data that I see during training. So I collect more data during training, I can push these things down. The bad news is I have this implicit bound, right, where this thing that I actually care about bounding shows up on both sides. However, hopefully I can convince you that if you stare at this long enough, if I make this term small enough, then I can invert this and actually get something meaningful on the gap. Right? And if anybody here is coming from a robust control perspective, this is basically a small gain type argument. Right? And that's exactly what we did. And what we showed was we defined this thing called tassel, or Taylor series imitation learning. And what we showed was that to ensure this small imitation gap, rather than just having the expert policy match and the test policy match, we want their higher order derivatives to match as well. And not only that, but like how high up this Taylor series expansion you need to go depends on the underlying expert's robustness. So for example, if I have an insanely robust expert that attenuates small errors quadratically, behavior cloning works out of the box provably. A more realistic example would be, say, linear robustness. So if any of you know what a contracting system is, that would satisfy this. Roughly speaking, anything that's locally exponentially stable will have this idea, because we actually only need these properties to hold locally. Then you want to augment things with a Jacobian cloning term. In general, we can just show that I'm going to have a small gap with probably at least 1 minus delta if I have enough number of demonstrations. And at least for me, the exciting part here was that the enough number of demonstrations scales or varies with the underlying robustness of my expert. So there's a kind of manifestation both in the easiness of the learning problem in terms of the number of terms in the loss function, as well as the amount of data that are reflective of the underlying expert robustness. And then very quickly, let me just show you experimentally what this looks like. We ran this on a bunch of Mujoko environments where we've informally ordered them from more robust to less robust. To get our experts here, we just used RL to get our hands on an expert. And so what I'm showing you here are behavior cloning, Dart, the offline approach, and Dagger, the online approach, with just the standard loss function and augmented with a Jacobian loss function. So what you'll notice is on the far left, the swimmer environment, which is like literally the most robust thing you could imagine. It's a worm swimming on the floor in a viscous fluid. Can't really think of anything more robust than that. You don't have to be clever, right? It just works. However, as you move farther to the right, you look at these more complex systems like half-cheat or humanoid, see there's a big win in terms of just including this Jacobian loss term. Right? And kind of coming back to this idea that what all these different IL algorithms are doing are trying to teach the learned policy how to recover from errors. I think of this Jacobian matching as just teaching these policies how to recover in the same way the expert does locally. Right? Good. So if we come back out to our informal meta theorem, what we've shown here is that controllers that are incrementally robustly stable are also easy to learn. Can I have 2 minutes? Would that be OK? Yeah? Thanks. So I just want to show you an idea of taking these ideas. It's a robotics seminar, so I feel like I have to show you some robotics experiments. And the idea here is just this general kind of philosophy of endowing learned components with this delta ISS property. So here, we're considering learning from human demonstrations in HRI settings where we want a compliant robot. And working with my collaborator, Nadia Figueroa at Penn, the approach here is to learn a vector field from a small number of demonstrations via kinesthetic teaching. So in this case, this neural ODE, the F theta, is learned from 2 or 3 demonstrations. And really, it's overfit to those demonstrations. But we augment this with a control theoretic term in red that shapes this vector field away from the data. So this allows us to get kind of the best of both worlds. And I just want to highlight very quickly here, on the left, you'll have a demonstration where there is no correction term. And on the right, there is a correction term. And you'll see, because there's such a small amount of data, on the left, there are these spurious attractors that if, let's say, a human comes in and moves the robotic arm away from its nominal path, it'll get stuck somewhere, right? Because it had no data, and who knows what the neural network is doing. And here, all we're doing is augmenting this vector field to satisfy this delta ISS property with respect to the nominal behavior. And you see you get exactly what you'd like. OK, I'm always overly ambitious and try to cram too much into a talk. So unfortunately, I think we're going to have to skip the talk, the component on multitask learning and big data. I'll just say that all of the really exciting things that you're seeing happening in foundation models and LLMs and all those kinds of things, we're starting to develop a theoretical underpinning of what these kinds of questions might look like when the data is generated by robotic systems, for example. And with that, I just have to put this slide up here to thank my fantastic collaborators, both current and past students at Penn, postdocs, and colleagues. And I'll leave up a slide here that has relevant references. Thank you very much. Happy to take any questions.
Wonderful. Thank you, Nick, for the fascinating talk. We have time for maybe one or two questions before we wrap up. So I guess now I've put a lot of pressure on whoever's asking those questions. All right, great.
Thank you for a wonderful talk. So just a very small question about the delta ISS approach. So how do you obtain the derivative with respect to x for export policy?
Yeah, perfect. I was hoping somebody would ask that question. I always leave that there as a dangling one.
Right,
No, that's a great question. So there are certain settings where you can just query it. So for example, if my expert is ILQR or nonlinear MPC or something like that, I could actually get my hands on it. If my expert's a human, probably won't be able to get my hands on it. We also do have results that show that you don't actually need to get it exactly. You only need to be able to approximate it to a certain degree of accuracy. So you can use first-order difference methods. And you can also use things like sketching, statistical kind of tricks to reduce the sample complexity and how much data you need to collect. But in general, this is not a fully general or generally applicable algorithm. At least from my perspective, the algorithm is cute and it's fun and it works well in the settings where it is applicable. But at least for me, the more important message of this component is there is a clear connection between the underlying expert's robustness and the corresponding hardness or easiness of the learning problem. This is just a sufficient condition, right? I'll just add a follow-up question and answer to that, which is, one thing you might be wondering or you might be asking is this even the right level or layer at which to do imitation learning? Should I be doing imitation learning at the torque level, or should I be doing it at the behavior level? And then have that connected up with low-level PD controllers or something like that. Turns out in that latter setting, things become a lot cleaner and a lot easier to analyze. But yeah, that's a fantastic question and perfectly valid to ask. Yeah.
All right, great. Maybe I'll jump in with a high-level question, but still somewhat mathematically grounded, which is, in the first part of your talk, you were giving these really beautiful and sort of elegant bounds about how you can decompose the hardness of learning and control a system into how hard it is to actually control the dynamics and how hard it is to identify the system. Now, in linear systems, we are extremely lucky that we have this thing called the separation principle that allows us to completely separate the problems of figuring out what the system dynamics look like and then controlling them once we have a good sense of what they're like. What I'm guessing is that once we move out of linear systems domain, that bound will not be as cleanly separable because learning what the system looks like and learning how to control it are going to be coupled together. But do you have a sense of how quickly this goes away, or whether there's a broader class of systems where you can still say something using those two separate terms?
I mean, that's a fascinating question. So I guess the first thing that I'll say is that I don't think that those kinds of questions are going to be answered in the imitation learning setting. That's just not really what we're trying to do. We're not trying to learn anything about the system. We're really just trying to mimic the policy. In general, I think, I'm sure that there is an intermediate class of systems, let's say piecewise linear, where maybe we can get some kind of local information that decomposes in that way. In general, I don't know what that would look like for nonlinear systems. I think it's a great question. And I think it would help us understand a lot of what's going on. model-based RL. If there are any model-based RL experts in the room here, maybe you have an opinion on this, but I think that's where that question would really come up. I guess this isn't exactly the question you asked, but what I will say is that for nonlinear systems, it's way too easy to cook up hard systems, right? And at least my take on why model-based RL has been as successful as it has been, despite all of these challenges, is it's not actually trying to learn the true model of the system. It's trying to learn a model of the system that's task-driven, right? So this idea of control-oriented or task-driven identification, I think, is really kind of what allows you to get around these kind of hardness results, and also offers a degree of interpretability. Right? It's not the interpretability that you just mentioned, but rather it's kind of the interplay of, let's say, model mismatch with task composition. And I'll just plug my student's paper at CDC on active learning for control that does exactly that.
Awesome. I'll have to read it. All right, wonderful. Well, let's thank Nick once again.
Thanks, everyone.